In this lecture, we're going to discuss a few more things we can do with sets. For example, the power set, the product of two sets, and a few other ideas. So let's start with the idea of the cardinality of a set. Cardinality of a set. Um, and so we define the cardinality of a set. Um, we use a symbol, these absolute value bars. So if my set is S, we say that the cardinality of S, that's how you read this, cardinality of S, um, that is nothing more than the number of elements in the set. So it's the number of elements in S. Well, for example, we could have, let's say, S is the set 1, 2, 3. Well, then the cardinality of S is 3 because there are 3 elements. So cardinality is just another word for size, essentially. Have to be a little careful. So just as sort of a trickier example, we could have this set with 4 and then the set containing 2 and 5. So if you'll remember, a set like this only has 2 elements. It has a 4 and it has a set containing 2 and 5. Those are 2 elements. So this one has cardinality 2. We can have infinite sets, and this is where so this concept seems simple at first, but it gets a little bit tricky when you're talking about infinite sets. For now, we're just going to say this is infinite cardinality, so infinite. But later, we'll actually we'll dive a little bit deeper into this concept of the cardinality of an infinite set, and we'll actually see that there are even ways of distinguishing between different sizes of infinity. Also, just to kind of make this point again, if for example, let's say I have S and I put another 1 there, well, this is kind of a trick question. A cardinality is not 4, it's still 3 because this set is actually the same as that because you'll remember sets, we don't count to repeat. So this is actually just a set containing 1, 2, and 3. So that's cardinality. Next thing we can do is, given any set, we can take the power set of a set. And we denote that like this. The script P, and then S is my set. And so the power set, and yeah, this is called the power set, that symbol. The power set is just the set of all subsets. The set of all subsets of S. For example, let's say we take one of our sets up here. Let's do this trickier one. So let's say S is this one, 4, and the set containing 2, 5. Well, what are the subsets? They are, remember that the first subset you should always think of is the empty set. The empty set is a subset of any set. You can take no elements. I can have the set containing 1 element. I can have the set containing that element. I could also have the set containing that element. And that would look like this, right? Because it's a set is a subset, so it's a set containing this element. And that element is itself a set. And then I could have the entire set S. That is another valid subset. So we see there are 4 things in the power set of S. This is the power set. It's another set consisting of all the subsets of my original set. Let's do another example maybe over here. So let's say my set is 1, 2, 3. 3, sorry. That's my set. Well, then the power set in this case is going to be, let's try to list them all. So again, I have the empty set. I have the subset containing 1, the subset containing 2, so I can have a 1-element set with any of my 3 elements. Now I can take all the sets with 2 elements, and I should for the power sets, all the subsets. So I could have that one with 1 and 2, I can have this one, and I can have this one. And then the final one is the set with 3 elements, and there's one of those. So there we go. And you'll notice something here. So this one has size 8, right? This one has size 4, and it turns out it's always going to be a power of 2. And the reason for that is for any subset, we can either have we can have that element. So for example, we could have this 1 in the subset or not have that 1 in the subset. And then we can go to the next element and say, okay, we can either have that 2 in our subset or not have the 2 in the subset. This 3, we can either have that 3 in the subset or not have the 3 in the subset. And then we can generate all our subsets that way. So there's a binary choice for each element, whether or not to include it in the subset. So the cardinality in general of a power set, so if S is any set, let's say a finite set, it's fairly obvious that if S is infinite, the power set will also be infinite. In fact, it'll be more than just, it'll be, if S is countably infinite, the power set's going to be uncountably infinite. But we'll talk more about that later. Yeah, the size of the power set is always going to be 2 to the number of elements in my set. So there's a formula for the cardinality of the power set. And also, I just want to note, sometimes you will see the power set denoted as, so sometimes we'll use the symbol 2 to the power S, like that, to actually denote the power set. You often see this in books, the power set. So either this notation or that notation. And now you get a better sense of, I think if I introduced it using this notation, you'd think that's a bit strange. But now that we see that powers of 2 definitely has something to do with it. So this denotes the power set. The next set construction we can do is we can look at the product of sets. And so this one is, we need 2 sets to define this one. So given sets A and B, let's take 2 sets. So we'll take set A and B. We can well, before we define a product, actually, let's define the idea of an ordered pair. So given sets A and B and elements, so let's take an element of A, let's say little a is in A and little b is in B, we can consider the ordered pair. And an ordered pair is just kind of what you're used to. It's you use it's called parentheses, and you just list your elements inside. So for an ordered pair, we use these parentheses rather than the brackets. So this is not a set, it's just a pair, and it's an ordered pair. So order does matter actually in our ordered pair. And the product is actually nothing more than the set of all ordered pairs. So the product, and we use A cross B, so like A times B, like that. And again, for now, I mean, I don't want you to think about this as multiplication. You're not multiplying the sets. The things in this product they're just ordered pairs. So I'm not multiplying things together. We're going to see why we use this notation though. But the things by product just look like ordered pairs, where a is an element of little a is an element of a, and little b is an element of b. But yeah, of course, you might wonder, why is it called product? What does it have to do with multiplication? So I think we'll see in an example or two. Let's take the example A. So we'll take two sets. We need two sets to form the product. You can always take a product of a set with itself. Let's do two different sets in this example. Let's do actually, let's do something totally different. Let's do like smiley face, just to show that this is a very general construction. So smiley face, frowny face. Well, what is the product? Let's write down the product. So A cross B in this example is the set of all ordered pairs. So I have all possible ordered pairs. So I can have one with the smiley face. I can have two with the smiley face. 3 smiley face. And then I can have one with the frowny face. And then 2 and 3. I think I got them all. Okay. And you'll notice something. What if you consider the cardinality of all these sets? So just note that the set A has cardinality 3, the set B has cardinality 2, and the set A times B has cardinality 6, which is 3 times 2. That's always going to hold as long as these sets are finite. You can get the cardinality of the product just by multiplying the cardinalities of these. And again, there's a good reason for that. We have sort of 3 choices for our first component, right? We have 2 choices here for our second component in this example. So the total number of pairs can be 3 times 2, so those choices are independent. Right, but note that the order matters here, right? So for example, a note, smiley face, comma 1 is not in this product. It's not in A cross B. That's actually in B cross A. But it's not in A cross B. The order is going to matter here. Products come up all the time. You've already seen products, actually. For example, this is kind of the standard example where you've probably seen ordered pairs. You could have R cross R. R is the real number line. I have another real number line, and the product is actually going to be all of 2-dimensional space, because this is all the ordered pairs, x comma y, for x in R and y in R. So let's write it like that. And it's a product where both of these are the same. Same factor here. This is also called R2. So you can use this exponent notation. So R2 means you take the product of R with itself. And there are so yeah, this is just our standard two-dimensional coordinate plane. And there are various subsets of this, right? So for example, I could have a line going through here, and the graph of that line would be some points x comma y that lie on that line, but not all of the points. And so that would actually be a subset of the product. Okay. These are both going to be very important later. We can also consider, another thing that's going to be important for us is the product of more than just 2 sets. So we can also consider the product of more than 2 sets, so the product of many sets. For example, the one you've probably seen is Rn. That's just R cross R is ordered n tuples. Cross R n times. n times. So in general, if you have sets like A1, A2, up to AN, you can take the product of all of those. And so elements in this product would look like, how should I do this? Actually, you don't usually write a comma. You usually just put the dot, dot, dot in the middle like that times AN. So I can have a lot of different sets and elements in here. What would they look like? They would look like some a little A1 and A1, comma, some A2 and A2, comma, and finally some AN and AN. So ordered n tuples of elements, one from each of the sets in the correct order. And while we're at it, we can actually, while we're at it, we've already seen some other set operations like the union and intersection. We can actually take unions and intersections. So we can take unions and intersections of many sets, just like we do the product. So for example, we can do A1 union A2 union, etc. And we can do A1 intersect A2 intersect, etc. And there's actually shorthand notations for these. We don't have to write this out every time. But before we go there, I should just so let's remind ourselves what is this symbol. So it's it's elements are in this union. If we just had two, they'd be in this union if they're in A1 and A2. Or A2. So if I'm in A1 or A2, I'm in A1 union or A2. So to be in this entire union, I just need to be in at least one of the ANs. So what is this? This is nothing more than it's a set of all x such that x is in a I for some I. And then this one down here, the intersection. Well, what if we just had two? These would be the things that are in A1 and A2. If we have multiple sets in our intersection, well, what is this? This is just a set of all x such that x is in AI for all I. And what do we mean all I? Well, we mean all I from 1 up to n. In general, we're going to have some indexing set. So we're going to take, let's say, for example, capital I might be the numbers 1, 2, 3, all the way up to n. And this will be our indexing set. And this is just how we've been using subscripts, essentially, to denote these sets. And so, yeah, as I mentioned, there's some shorthand notations for this, and that looks like this. So if I want a union of a bunch of different sets, I want to sort of glue them all together, I can write like this. So I from 1 to n of A, I. That is shorthand for this. A1 union A2 union, etc. all the way up to AN. Okay. If you've seen this summation notation before, it's very similar to that. So I starts at 1, it goes up to n. And in general, I mean, what we might do later is we'll replace this with just a general indexing set. And we'll say I is some element of that set. But for now, yeah, we're going to have our indexing set just be numbers. So there's a union over multiple sets. We can do an intersection over multiple sets, and that So this notation is shorthand for, and you write a bigger symbol than you do here, right? So this one's this one's bigger than that. Yeah, A1 intersect A2, intersect A3, etc., all the way up to AN. Okay, and these notations are like probably if you've glanced at some advanced math books, you see things like this all over the place. So now you know what those mean. And again, yeah, this to be in this set, it means that we're in at least one of these. And to belong to this set, it means that we're in all of these. Okay, let's see, intersection. Okay. So rather than just end it here, I want to dive a little deeper into this concept. We can actually consider, and we will need to consider this later, we can even consider infinite families of sets. So infinite families of sets. So our indexing set might start at 1, 2, 3, and won't stop. It will just keep going. So our indexing set, in other words, will be the natural numbers. Okay, and you've probably seen that here when you've seen the summation notation. If you've seen that before, you can have infinite sums. So we can have infinite unions and infinite intersections. And these are kind of fun to think about. So let me try to think of an example. So here's an example. Let's actually try to figure out this set. I'm gonna let AI be. Let me call it AN. I'm going to let AN be the interval from negative n to positive n. I'm going to use the natural numbers as my indexing set. Now I've got a question. So what is the, let's do the, let's do the union from I equals 1 to infinity. So we have an infinite number of sets, AI. So what is that set? How do you describe it? Oh, and by the way, so yeah, what is this? This is literally just a closed interval from n to n on the real number line. So just take all the numbers between negative n and n inclusive. So, for example, if I have my real number line somewhere, maybe this is 0, negative 1, negative 2, 1, 2, etc. What are these sets? Well, A1 is going from negative 1 to 1, so I'll look like that. A2 is going from negative 2 to 2, etc. A3 is going from negative 3 to 3. And I'm unioning all these sets together. I'm taking a union of them all. And so if I just had the first three, the union will be this whole thing, right? Because it's all the points that are in at least one of them. So this one's bigger than the other two. It's actually a superset of these two. It's the opposite of subset. So it includes these two. So if I just had 3, then yeah, I would get this entire interval here. But what if I let this keep going? Well, you're actually going to get the entire real number line. So this is actually all real numbers. And that's because consider any number, like write down any number, even if it's a really big number. At some point, you're going to get in one of these intervals, right? And now, because I'm in at least one interval, I'm in the union. So this is actually the entire real number line. Which is rather interesting because all of these sets themselves are just intervals. So they're not infinitely long intervals or anything like that. But the union of infinitely many of them, can easily be the entire interval. Here's another fun example to think about. Let's let, maybe define a slightly different one. So let's let Bn be, I'll do the closed interval from 0 to 1 over n. Okay, 0 to 1 over n. Let's do it. open interval over there. I don't think it's actually going to matter, but so here's a question. What is the intersection, infinite intersection, equals 1 up to infinity of the bn's, so bi. All right, because I want it to be b1, then b2, then b3, so this has to match this variable. This is counting up from 1, 2, 3, 4, all the way up to infinity. So what's that set? Well, we can try to draw a picture here. So, well, what do we have here? In this case, we have 0 here, and 0 is in all of these sets. Because 0 is in all of these sets, right? This is a closed interval. I'm including 0. Because 0 is in all of these sets, I know. So since 0 is in bn for every n, just based on its definition, I know 0 is in the intersection. Right? Because that's what it means to be in the intersection. I'm in every single one of the bi. And I am. You tell me a bi, I can show you its formula here. 0 is in it. So 0 is in all of them. But I claim that no other number is in all of them. 0 is the only number in all of them. Right? And it's because, well, maybe b1 is here. And so my b1 is going to be 0 up to 1. b2 is going to be 0 up to a half, right? 1 over 2, etc. And 0 up to 1/3. And so I've got b1 like that. b2 is going to be smaller. b3 is going to be even smaller. And they're going to get smaller and smaller and smaller, right? So that's the picture. I'm taking an intersection. So I need to be in all of these sets. All of these sets in this intersection. In order to be in the intersection itself. And you might get the feeling that there can't really be anything else, right? You could say, oh, there may be some numbers really close to 0. But you tell me the number, so like you tell me the number x, I can tell you x is definitely not going to be in this intersection. Why? Well, so given any x greater than 0, there's going to be some n, maybe very large, but there is an n such that, might be a very large one, but I can guarantee that 1 over n, this sort of upper bound, is going to get smaller than x. I can guarantee that. And the reason why I can guarantee that is, well, if we rearrange this slightly, what we get 1 over x is less than n. So 1 over x is some finite number. So some finite number. So all I need to do is pick an n large enough, larger than that finite number, whatever this is. Okay? And for sure that n is going to be in my indexing set. So I just need to pick some integer n, or some natural number n that's large enough to be bigger than this 1 over x, whatever x is. And because I can do that for any x, I can guarantee that any x greater than 0 is not going to be in this infinite union. And so it turns out this infinite union, what's the answer? The answer is only the point 0. 0 is in here because it's in every single one of the bn. So it's only the point 0. Okay, well, let's end it there. If you want something else that's maybe interesting to think about, if you change this to an open bracket, so you don't include 0, well, then it turns out the answer is actually just going to be nothing. So the empty set. This is not the empty set. This is a set containing 0. But yeah, if you switch that to a open interval, sorry. Well, you're not going to get anything larger than 0 by this argument, but also 0 is no longer in this set. So you actually just get nothing, which is rather interesting because each of these is overlapping with something, and these all have non-zero length. So it's rather surprising. But yeah, you actually get nothing in the infinite intersection of these sets. Okay, so those are some set operations. Again, these are going to be very important for us later in the course. Now is a good time to introduce them. Thanks for watching.